Good day, everyone. We are from two going to app report that is Bernoulli's principle. My name is Sarinda son of Kartiki. Today I'm going to explain about the introduction part. This experiment intend to examine the performance and efficiency under varied operating condition. There are two aims in this experiment. First, the experiment aim is to create and access comprehensive measurement technology and experimental process for fluid flow. The second experiment purpose is to test Bernoulli's principle experimentally for viscous and incompressible fluid flow. In the end of the experiment, the result will be displayed in the graph. The next part is objective. The objective of this experiment is to design and evaluate complete measurement technique and experimental procedure for fluid flow. The second objective is to verify Bernoulli's principle experimentally for viscous and incompressible fluid flow. The third one is to find the value and understand the relationship between the static aid, dynamic aid, and total aid in Bernoulli's experiment. The third part is the background and the theory. The experiment is to test and verify the Bernoulli's principle in fluid flow. The principle is named after Daniel Bernoulli, that is the Swiss mathematician and physicist. He is play a huge role for his application of mathematics into mechanics, especially fluid mechanics, and for developed work in probability and statistics. In this experiment, we had been given the task to verify and test the Bernoulli's principle on the fluid flow. That's all from me.
My name is Ilantarian Ganesan, MA18057. I'm going to explain about Chapter 2 Theory in the experiment of Bernoulli's principle. Bernoulli's principle. Bernoulli's principle is an important theory in fluid mechanics. Involves a lot of knowledge of fluid mechanics. Bernoulli's equation solve the problems of force, energy, which is often involved in engineering practice. The application of the equation runs through the course of hydraulic mechanics. In the Bernoulli's principle, the most important uh, aspects are energy, fluid, and formula. Venturimeter. Venturimeter is a measuring device that is usually used to measure the flow of a fluid in the pipe. It is also used to increase the velocity of any type of fluid in a pipe at any particular point. The pressure in a fluid moving through a small cross-section area drops suddenly, leading to an increase in velocity of the flow. The fluid of the characteristic of high pressure and low velocity gets converted to the low pressure and high velocity at a particular point and again reaches to high pressure and low velocity. The point where the characteristic become low pressure and high velocity is the place where the Venturi flow meter is used. On the figure there, we can see the Venturi meter, the safety valve, manometer, rotameter, elbow, orifice meter, Venturi meter, manometer tappings, and gate valve were all connected to create a Venturi meter. Next, this is the formula. The formula and the pipe, as I explained before, is here. The P1 is pressure energy and 1 over 2 PV square is kinetic energy per unit volume and rho GH is potential energy per unit volume equals to P2 plus 1 over 2 PV square plus rho GH. The often cited example of the Bernoulli's equation or Bernoulli effect is the reduction in pressure which occurs when the fluid speed increases.
Proceed. Hi, my name is Nur Aisha binti Sadun. My meeting number is MA18049. Now I would like to continue this presentation with chapter 3, which is methodology. So this chapter consists of apparatus, schematic diagram, experiment procedure, and the precaution step. So basically, this is the apparatus that we needed in the experiment, which is hydraulic bench and Bernoulli's theorem demonstration units. So we move to the schematic diagram. So here, we can understand that that the total pressure head can be measured at the pitot tube, and then the elastic head measurement can be measured at the multi-tube manometer. So here we can see that the multi-tube manometer consists of 6 different points, which is it refer to the 6 internal diameter, which is here 0.1 until 0.6. Then we proceed with the experiment procedure.
Step 1. Turn on the vent valve. Next, turn on the pump and adjust the volume flow rate. After that, close the hole before start the experiment. Step 4. Measure the flow rate on the volumetric tank. Measure the static head through the multimanometer. And lastly, the total pressure can be measured by the pitot tube measurement.
Okay, lastly, I will talk about the precaution step of the experiment. First, we need to measure the reading at the perpendicular angle, which is the eye must be 90 degree to the reading to the meter. Then second, double check all the measurement to ensure the accuracy. Third, precaution is focus and alert all time during the experiment to ensure this experiment can be done successfully. And lastly, conduct the experiment many times to get an average value of data collections. So from the data that we collect, we can get the average value.
Assalamualaikum and good day. My name is Nuraina. So, moving to the chapter 4 for the result and discussion for Bernoulli's principal experiment, the given value for the volume is 5 liter and the time given is 19 seconds. So, from 5 liter, we change the value to meter cube and we will get 0.005 meter cube for the volume. Following that, this is the given value for static head and the second table is the value for pitot head in unit millimeter. Next, this is the given internal diameter for 0.1 to 0.6. Now we will discuss more about the formula and sample calculation for 0.1. For the first step, find the flow rate by using formula Q equal to V over 1000 and divide by the time given. And the value flow rate gain is equal to 0.0002632 meter cube per second. In second step, we calculate the area by using the given internal diameter and record the answer. Then, Step 3, Step 4, Step 5, Step 6 and Step 7 was calculated by using given formula and the data obtained was recorded in the table below.
Assalamualaikum and hi everyone. My name is Nur Shafika binti Nur Sofyan and my matrix number is MA18034 and I'll be continuing the presentation with the discussion part. So for this discussion part, we have represent all the calculated data into the graph, and for this first graph, it is the variation of head against the point or area. So each of the point is representing a different cross-sectional area because it have different internal diameter of the tube. So the variation of head that I mean is static head, dynamic head and total head. And as we can see that dynamic head is inversely proportional with the static head. And for the total head, it placed in the on top of the other graph because total head is the sum of the dynamic head and the static head. So next is graph 2, which is the graph of velocity against area or point. So as we can see that the highest velocity is located at point 3, which is point 3 is the smallest cross-sectional area compared to the other point. And we can conclude that the velocity is inversely proportional to the area, which is the smaller the area, the higher the velocity. So this is graph 3, which is the graph to represent pressure versus point or area. And in this graph, we are using the dynamic pressure, which is dynamic pressure is against or opposite to the static pressure. And the characteristic of dynamic pressure is it is inversely proportional to the area, which is the smaller the area, the bigger the dynamic pressure. And as we can see that the higher pressure is located at point 3, which is it have the smallest cross-sectional area. So this will be the last graph, which is the comparison in between the velocity and the static pressure. And as we can see in the graph, that the velocity is inversely proportional to the pressure, which is at point 3, we can see that it shows the highest value of velocity, but for pressure, it have the smallest value. So therefore, we can conclude that from this graph, we have fulfilled the Bernoulli theorem, which is when the velocity is increased, the value of pressure is decreased. So that's all from me. Thank you.
As a conclusion, we can observe that the proportion of the static and dynamic aids are inversely proportional. The dynamic aid on the other end is inversely proportional to the cross-section area. Thus, as the cross-section area decreased, the dynamic aid increased. The total aid is the sum of static and dynamic aid, which is why the graph is greater than dynamic and static aid lines. Other than that, we are able to define the terminology like pressure aid and velocity aid. From that, we can conclude that velocity is inversely proportional with the pressure. In foregoing of all of this result, we are able to say that Bernoulli's theorem is verified. That's all from our group. Thank you.